Okay. I see. Okay. All right. So I think you're familiar with this chart I shared with all of you. So we are starting this course, the Study Abroad program, and in particular we are looking at the courses that you see over here. Structural analysis is what we are having the first class for now. So my name is Dinesh. I've been a faculty member here for almost 2 decades now, and prior to that I did my PhD at Georgia Tech, and my advisor at that time was Professor Dr. Hodges. He passed away a couple of years back, so he was one of the celebrated professors there. Talked about as the father of rotorcraft aeroelasticity and structural dynamics, highly regarded in the community. And a lot of what I learned on many subjects, including structural analysis, is from him. So I kind of dedicate this course to him. As you know, we'll be meeting for about 1 hour 45 minutes on Mondays and Thursdays. So that's about 3.5 hours a week. Which means for 10 weeks it would be about 35 hours. As I already told you in one of the emails, we'll not be having any exams as such. So all the 10 weeks, so all the entire 35 hours will be dedicated to interactions. And it will be two-way, as I said in one of my later mails regarding the assessment practice. So I'll be expecting some of you to come up here on stage and talk through what you have done as far as the previous homework is concerned. So, I want this to be kind of a fun exercise so that we all learn together. I also would like to learn along with you. And so we would like to use some of the current methodologies in terms of taking advantage of what is in the developing situation, so that you're all kind of ready when you graduate either for the industry or for further higher studies. You're prepared for what the world has changed to from the time you even a year or two back when you entered undergrad program at Georgia Tech to when you graduate. So things are changing quite rapidly, and there are lots of precedents to what has happened in the past as well. For example, it was not very long back that some of the richest people were those with most muscular strength, because most of the jobs involved a lot of physical activity, and the more muscular people were, they tended to get more jobs. Over a period of time, machine development came up, in particular, for example, cranes. So people could lift only up to a certain amount of weight, transfer it to a certain distance, but with cranes or even large ships which carry huge tonnage of cargo from one nation to another, things have changed so rapidly in terms of replacing muscular physical activities with machinery. And in the last almost 7 decades, you have seen a lot of progress in terms of a lot of computations that we have been doing manually, analytically. That also has gotten onto computers, and a lot of those jobs have become irrelevant. So people have had to kind of reinvent themselves in order to be suitable for the new developing situation. And those who don't do that tend to get left out or fall back in the society. So keeping that in mind, I just wanted to take advantage of the fact that we have a small group. It's very difficult to do this when we have a regular class. Like, for example, if this whole class was filled, it becomes a little more challenging to do what I'm planning to do over here. So we want to take real advantage of that, and which is what I also told you over the email. So as I mentioned, there are lots of these large language models, both from OpenAI, which is now licensed by Microsoft through the Edge browser, and also you have Google developing its own Bard and Palm 2 and things like that. There are many, so we've gone, even though ChatGPT has been a few months old, we've gone a long way from GPT 3.5 to 4. But the point is that jobs like mine, teaching to you, would over a period of time become irrelevant, or at least it wouldn't be the way we are doing it right now, or we were doing it in a few years back. So the question is, how do we reinvent ourselves for that kind of new academic jobs as well as aerospace industrial jobs? One of the things is that, like for example, when you don't understand something in the course that I'm teaching, you'll be asking me questions. I'd really prefer that to be interactive, this whole session, and I'd be answering. But it's very much possible, even in the fields that I have specialized or I've got a PhD in, the AI, because of the amount of source of information it has and the way it processes it, could probably be giving you even better answers or more relevant answers than I do. But the question is, are all of its answers right? No. There are lots of hallucinations and many other negative aspects of what AI program can do, at least at the stage at which it is, which means that there is still a lot of intervention that is required from the user, both at the input level, where what is known as prompt engineering is coming up, and at the output level in terms of post-processing the result. So you asked a question in a particular way, it is answered in a particular way with certain settings for how challenging you would want the outputs to be. But then if you ask the same question at the same challenge levels, you could get different results and more probably optimal results, or the way in the direction that you want it to. So the question answer methodology is something that we in India have been very, very proud about. The Indian culture for a long period of time has had this Upanishadic way of learning in the Gurukul system, where students go to a teacher, ask a lot of questions, very intricate. Some of them, once they get the answers, it might sound very silly, those questions, but when they were not yet answered, they were not silly. And a lot of people, not just that student, but many other students over the centuries kind of benefited from that. So in a sense, we are getting towards that in terms of prompt engineering, where the way we ask the question, the way we first think for ourselves and then put it out, and then how do we assimilate that answer, how do we put that into practice in a day-to-day job when we have a certain task in the aerospace industry. These are the kinds of things that we need to kind of be best at. And this particular course, structural analysis, is a really ripe candidate for bringing in that kind of methodology in teaching, because there are many, many different ways in which the same structure could be analyzed, or the same methodology can be applied to many different kinds of structural components. So which do you choose? When do you choose? How do you choose? And how do you interpret the results? What kind of inputs do you have to give? These are the kinds of questions that we have to be more aware of. Any problem, as you know, there is two parts to it: the problem definition, where you formulate the problem, and then there is a solution methodology to it. The solution methodology for long has already been taken over by software. As long as you have chosen the right kind of software and the right kind of options that you have chosen within the software in order to run that, the solution is going to be more or less taken care of. But if your problem definition or formulation itself is going to have certain holes in it, then no matter how good a software you have, how good a methodology you have, it's not going to be of much use. So the focus in this course, unlike in traditional structural analysis courses, will be on the problem formulation. I want you to make sure that the problem that you're posing to a computer or to any analyst, or if it's even an experimental problem, the kind of design of experiments that you come up with, are you giving the right kind of definition so that the output will be eventually beneficial to what you are looking for. So that is the direction in which I would like this to go, and which is also why we have this office hours on Thursdays in the morning, 11 to 1, and you can seek an appointment. It's over MS Teams. Have you three been able to access the MS Teams that I created for this particular course? Yeah? No? Okay. So I think one of you has. Maybe we could help your classmates to get onto that, so that it will become a good communication platform for me. I know most of you are familiar with Canvas, which is what you use for a lot of other Georgia Tech courses, but in IISc we predominantly use Teams, and I'd like you to kind of familiarize yourself with this platform as well. It's only for the office hours because the classes will be face-to-face like this throughout the 10 weeks. So I'll be meeting you every week related to this. The other important point of this whole study program is this weekend that I really want you to utilize in an appropriate way. Of course, you would have, based on your own personal preferences, a lot of things that you would like to see. But as engineering students, I want you to look at some of the antiquity in terms of engineering structures that have been created in India when the kind of tools and equipment that we had were very, very different or rudimentary from what we have today around the world. So with that kind of knowledge systems and tools and techniques, how people have created such massive structures, many of them civilian structures, but also there are certain transportation modules and things like that. There are places where you can go visit that. I will not be taking too much of the time of the course in terms of talking about this, but every Monday and Thursday I'm in CVH for lunch between these two courses that I teach, and therefore you're welcome to chat with me informally during that or after that or even during these office hours, and then we can see how we can, I can probably give you some suggestions on places to see, or if you already have places to see in your list, what specifically to look out for and things like that, in case you need inputs like that. But of course, again, there is the LLM for that as well. So you could always ask ChatGPT or something for that. But keeping that aside, I think this is kind of taken care of. Also, it's important, it's because of that reason that I call this the Indian navigation for Georgia Tech students, because the course itself, not just the two courses that I'm teaching, but all the other courses that are being taught are going to be very similar to what you would learn there as well. But the way we are going to be interacting and the way we are going to be evaluating and also the weekends, the way you're going to be exploring other aspects of life and knowledge systems, I think that's what is going to add value to your study abroad program, and I really urge you to make the best use of it. Okay. Yeah, I've already introduced to you Chinnababu, who's here. So he's one of my PhD students. You have his email in the mailing list that I sent to you, so I'm not listing it here explicitly. Also, he's on the same team as all of you, and so feel free to interact with him when you need to. Our lab is called the Nonlinear Multifunctional Composites Analysis and Design Lab. So very, very relevant to the kind of course that I'm teaching over here right now, because there is analysis and structures is what we are primarily considering over here. And most of aerospace structures today are made out of materials known as composites, primarily to reduce the weight, but there are many other reasons as well. We'll see some of them shortly. But in the lab, as far as research is concerned, we focus on nonlinear models for it, which are much more reliable in terms of accuracy levels. At the same time, we use certain state-of-the-art mathematical techniques to arrive at those models, both for analysis as well as design, which are not only accurate but also efficient. Usually it happens that very efficient models are inaccurate and very accurate models are inefficient, but we tend to see, based on the user's requirements, if they want an accurate kind of an analysis, what is the level of accuracy they want, in what kind of results, and for that, what is the mathematical guarantee in terms of the most efficient algorithm that you can have. This is the goal with which we work on various aerospace applications, both in analysis and design. So analysis is something where you break up things into smaller parts. For example, so structure, you look at structural components and then you try to delve deep into it and try to understand it in a better way. Whereas design involves a concept which is opposite of analysis, which is synthesis. So the intellect is usually more capable of doing an analysis, trying to break up things and trying to study each one of them in detail to go in depth. Whereas the design requires holistic thinking. You need the bigger picture, you need a breadth of knowledge along with the depth of knowledge. So that is where synthesis comes in, and the intellect can do only up to a certain level there, and yes, it gives the inputs for it, but to a large extent there's a lot of intuition and art involved in design. So that is where we as a human being can develop in a much more holistic way in terms of not just being like a computer in terms of mathematical capabilities, but also in terms of the art, the aesthetics, and also the synthesis of various concepts into an actual product, and eventually how it helps the society and the world at large. So that's essentially what we do at the lab at the research level, and we will do in this course at the teaching or academic and knowledge level. Also, I left out this particular thing. Typically, when you talk of structures, they are unifunctional, conventional, traditional structures in the sense that they are load-bearing. For example, this beam that you see over here, or a column that you see where the beams are connected to, those are essentially taking various kinds of loads, and they ensure that the building doesn't fall off, right? So, is the primary function of any structure that we are going to be dealing with is load-bearing, which means that it has to offer a certain level of strength, it has to offer a certain level of stiffness. So it should not be overly flexible, it should not be overly rigid. At the same time, you should be able to take loads up to a certain level, which is typically defined a little more than what is expected in the normal operation of that structure. For example, in most aerospace structures, the factor of safety is 1.5, which means you design the structure for 1.5 times what is the maximum which is anticipated using what is known as a Venn diagram or a flight envelope and things like that. We will look into what these things mean and what exactly they imply for us, the structural engineers, as we go forward in the future classes, but I'm trying to give you the big picture right here. So as I said, all traditional structures are unifunctional, but in the lab here we deal with what are known as multifunctional structures, whereby I mean that in addition to the primary function of load bearing, can this structure, let's say, have a function of energy storage? Can it do energy harvesting? Energy storage in the sense of a battery. So the structure itself is a battery, or the battery itself is a load bearing structure. Or energy harvesting in the sense that, let's say, certain wind energy or vibrational energy and things like that, is it able to harvest that? So for example, the fibers could be piezoelectric fibers, which can harvest the vibrational energy in some sense. It could be battery fibers, in which case you could have a carbon core which provides the primary strength requirements, stiffness requirements, and then there are layers around that which are solid state electrolyte and a solid state other electrode, be the anode or the cathode. So things like that, or electromagnetic functionality where the structure itself doubles up as a radar or as an antenna. So you try to bring in that functionality into it. So many, it's kind of the imagination is the only limit. One very popular multifunctional structure over a long period of time has been what is called a smart structure or adaptive structures. Like our body tends to adapt to the environment depending upon how hot it is, or different altitudes and things like that, with different pressure levels. We tend to adapt or to the seasons as they change and things like that. Similarly, the structure should adapt to the environment in terms of able to sense what is happening and actuate it itself in some way so that it is better performing for the new situation that is being created in a developing manner, almost on a breaking news kind of a situation. So that kind of structure where it is co-located sensing and actuation. So there is a structure, it can take a certain load, so it is load bearing because it has certain strength and stiffness, but at the same time it's able to sense how hot it is or how other kinds of environmental things, and then change its own capabilities by actuating itself in a particular way, changing its shape and or size, and then you have a much better response to the new situation that is developing. So these are the kinds of materials that we work on. So just to give you an idea of exactly what we do. Now, Already we talked about analysis in terms of breaking things and looking at it in parts, not just in terms of the structure itself breaking into components. For example, the aircraft wing can be thought of as made out of the aircraft wing skin, the upper skin, the lower skin, and inside typically a skeletal kind of a structure which has spars, a front spar, a rear spar, some stringers. You could have ribs which are transverse stiffeners, etc. We'll see pictures of that as we go forward in the course. You might have also seen it in other in different kind of situations, but we will try to look at it purely from the point of view of this particular course. Now, so one way is to break up things in terms of the structural components. Even just a single beam, in the case of aircraft, you have what are known as I-beams. So you have two flanges on top and bottom, and then you have a web in between, and which is typically what is called as a shear web. And these flanges are good at taking tension and compression. So if one takes tension, the other takes compression, then essentially you're taking care of bending as well. So there are many ways in which you can break up to what level you can go around breaking down a component. And then within that component, for example, if it's made out of a composite, it has multiple materials. You break it up into the matrix and the fiber and the interface between them, and how all of them together are acting in terms of providing us that primary function of load bearing. So these are the kinds of things that one way of analysis is. The other way of analysis is in terms of the model itself. Once you develop a model, the mathematics of the model can help you to decompose the problem. So you can decompose, for example, if there's a problem in which there is a spatial dependency and a temporal dependency. That is, it depends on, let's say, an x1 coordinate along the length of this tabletop, let us say, for example. It depends on x2 as well, which is along this direction. It also depends, let's say, if this I'm applying a dynamic load like this, it also depends on how it behaves. It also depends on the time. So in other words, these are three independent variables that you have in terms of the spatial coordinates and in terms of the temporal coordinate, which is time. So now once you have a problem like that, you end up with the governing equations that are there turn out to be partial differential equations compared to ordinary differential equations, where it depends only on one independent variable, let's say x1 alone. If it's a static problem, let's say, of a beam, and I'm trying to, let's say, or even an axial rod, to take the simplest case, and I'm trying to pull this rod, then everything is a function only of x1. The governing differential equation also involves derivatives only with respect to x1. So x1 is the only independent variable, and so you have what are known as ordinary differential equations. But once you want to model this not as a beam, let's say as a plate, then you bring in not only x1 but also x2 along the width. Now x1 varies, let's say if this is the length L and I put the origin in between, it varies from minus L by 2 to plus L by 2. Similarly, if the breadth is B, and origin is at the center of this, so x2 varies from minus B by 2 to plus B by 2. Let's say if this height is h, then once again the origin being at the center means that the domain of interest for us is x3 from minus h by 2 to plus h by 2. So essentially structural analysis, or any physics problem for that matter, involves physical quantities, and by physical quantities we mean there are boundaries. So there are boundaries. If you do not have boundaries, you get to what is known as beyond physical or metaphysical. What we are interested in is, in this course, is physical quantities, physical components, and almost all of physics deals with these boundaries. And these boundaries I talked to you about in terms of spatial boundaries. Similarly, there are temporal boundaries. Even for biological systems, if you take a particular living entity, it has a birth, it has a death. So in other words, there's a T0, there's a TF, the initial time and the final time. And so those become the boundaries from a temporal coordinate sense. From our own experience, we might experience space and time in different ways. But in reality, time and space, as far as mathematics is concerned, are both just say independent quantities of different kinds. And the governing differential equations, even for a beam which depends only on one coordinate, spatial coordinate, If it's a dynamic problem, it depends on another coordinate, which is time. So it depends on x1 and it depends on time. And the mathematics or the equations are kind of immune to what it depends upon. Those kinds of equations where more than one independent variable are there, which we call as partial differential equations, are usually a little more difficult to solve compared to the ordinary differential equations, and therefore you tend to see if you can decompose the problem. So analysis, as I said, involves not only breaking up structures into its components, but the materials into its components, fiber and matrix, for example, but also the mathematical model itself, which depends on both x1 and t. You can make it into two separate problems, one which depends only on x1, one which depends only on t, and therefore you have ordinary differential equations much easier to solve. So there are many different ways of approaching these problems, and we will see them as we go forward. But it's very important to understand all of this from this bigger picture that we are dealing with physics, a certain branch of physics which is mechanics, and for most of what we will do in this course is not dynamics, it's mostly statics, in the sense that the time will not be a very important variable over here, but many of the things that we develop can eventually be used as a starting point for dynamic analysis also, because in problems like these where you consider a beam, or in problems like these where you consider a plate or a shell, you will see that one dimension, in this case the thickness, is very small compared to the breadth and the length. In this case, the cross-sectional dimension, be it the height or the breadth, is small compared to the length. So when you have such a situation, the governing equations in the smaller dimensions stop depending on time, or their dependence on time is very weak, so that you don't have partial differential equations, in that you have only ordinary differential equations. But in this case, there are two dimensions in the small, which in the smaller sense, both the, if you're modeling this as a beam, you would see that the thickness is also small, the breadth is also small compared to the length, both are small. So in other words, there is no time dependence of the problem over here, or if at all there is a dependence, the dependence is very weak in terms of how the cross section deforms. But how the overall beam deforms in a dynamic loading situation, there is a lot of dependence on time. So if we break this problem into two parts, one is cross-sectional analysis, the other is analysis along the reference curve of the beam, then one problem will depend on time. Yeah, but the other problem, even if it's a dynamic problem that we are dealing with, may not depend on time to that extent. But that is also a partial differential equation, because two spatial coordinates are involved here. Whereas in a plate problem, the smaller dimension is only one, that is x3, the thickness, and therefore only ordinary differential equations are sufficient. Whereas here, even for statics problem, partial differential equations are required, because two independent variables are there. Both are of the same kind. It's not that one is spatial or the other is temporal. Both are spatial. It's x2 and x3. But once you have more than one, you don't have an ordinary differential equation. You have a partial differential equation, and you have to handle it in that way. So that's all that there is to structural analysis. Because it's an analysis, you're breaking into parts. Because it's a structure, therefore it's a physical quantity or entity, it has boundaries, and these boundaries are both in space and time, and therefore you end up with what are known as boundary value problems and or initial value problems. Boundary value problems are governing differential equations with certain boundary conditions, and initial value problems are again governing differential equations with certain initial conditions. You could have variations in this also in terms of what typical shooting method tries to achieve. There's a numerical methodology called the shooting method that if I want to fire at something, I want to ensure that the angle is right. So in other words, I want a certain final condition. Based on that, can I get the initial condition and or design this shooting element that I have, a gun or whatever, to make sure that that is achieved. So the whole idea is that there are certain known quantities or unknown quantities. You want to determine the unknowns in terms of the knowns, for which you need a black box, which is essentially your model, the mathematical model. And the whole process of this course in the rest of the 19 lectures will be towards developing such black boxes for various kinds of structures. Some could be what we call as beams, which predominantly bend in both directions. There could be torque tubes, which where a torque is applied and therefore it twists. It could be a rod, in which case there's a tensile load and it extends. There could be a column like what we have at the ends of the room. So you have a compressive load, and therefore once again there's an axial deformation as the primary response. But there could be couplings that are happening both because of the geometry as well as the kind of materials that we might use. We might see certain couplings. So even though I'm compressing, the shortening of this may not be the only response. It could end up bending, it could end up twisting and things like that. And in fact, it does happen, and certain parts of this course will be dealing with elastic instability problems, what is known as buckling. So essentially, when I apply a load beyond a certain value, even if the material has not failed, in other words, stress nowhere in this structure has reached a value which is close to the yield point of the material or some material failure limit, but still it could fail geometrically because it could be so flimsy that this could just snap through, which is what we call as one type of elastic instability. There are many others which are local instabilities occurring, etc. We will not go into the details of those because beyond the scope of this course, but in passing we'll mention when we reach there. So these are the kinds of things that will be covered in this particular course. If you have any doubts on what I have talked about till now, feel free to ask. Okay, so I think we'll move on. Okay, so as I said, you are familiar with the timings of this course and the days of and also the period during which we have this. These are all also like kind of boundary conditions in a temporal sense, that you have certain discrete values that you have, and once again the overall boundaries that you have. Once you start looking at it from that perspective, you see that it's actually either the day-to-day language that we are translating into the mathematics of the problem, or the mathematics of the problem that is translating into what we use in day-to-day. There is a lot of similarity between that. We tend to think as these are two different things, distinct things, but there's a lot of overlap in terms of how a human mind works, in terms of the different kinds of things that it experiences in life. So first we'll look at the fundamentals of what I call as flight vehicle structures. So, so there are structures because we are doing structural analysis, and those structures are part of flight vehicles. It could be aeronautical vehicles like a helicopter or a aircraft. It could also be a launch vehicle, a missile, or it could be a satellite. Or interplanetary orbital systems, or those which land on the planetary surfaces, it's like robots and things like that. Essentially, we are talking of things which at least partially fly, because even an aircraft, for example, there is a certain takeoff where it is like a ground vehicle, it is operating. So a certain portion of the motion or the movement of the vehicle is in terms of flying, either in air or space. So essentially we are talking of all those kinds of flight vehicles, and there's a lot of similarity, commonality in terms of what are the choices we make for rockets, some things which are similar in choosing the same for a helicopter, but there are also large differences, and so we will look at where those differences stem from, why you choose one material over the other for a particular application. And within the helicopter itself, the rotor, different parts of the rotor might be made out of different materials, of different geometries, and let's say the fuselage, different parts of the fuselage, the nose might be made out of a different material because it could be prone to, let's say, some impact loading because of crash possibilities and things like that. The landing gear could be made out of different material, etc. So we will look at all those materials as well. So the flight vehicle structures, whenever we say structures, it involves two aspects to it. One is the material that structure is made out of, and the second is the geometry of that structure. For example, this is a long, slender structure. You could have a very bulky structure like the civilian beam, for example. Whereas the spar, which is also a beam in an aircraft, but much made out of thin walled structures. So that is one of the primary differences you will find as we go to flight vehicle structures. You will find a lot of thin structures, both closed sections as well as open sections, and we will see where they get used and why. So that is the fundamentals of structures, both from the geometry and the material point of view. Then we will review some of the things that you have already learned as part of your stress analysis. So it will be a basic introduction to elasticity in terms of the stress strain components, the stress strain measure numbers, how they are related to each other, how in turn the stress is related to the loads, how the strains are related to the displacements or deformations and rotations. And then we will have an analysis of if those materials were made out of what is very commonly used in aircraft or aerospace industry today, composites. How do you analyze that? How does the analysis change? What are the new complications that arise, both in terms of when it is healthy and when it is close to failure? What kinds of failure can it encounter, which are different from the kinds of failure of a metallic structure? And then how you can probably deal with those failures or delay those failures, if not avoid them altogether. Then, as I said, in terms of the geometry, we have, even if you take the case of beams, you have either a solid cross section like what you see over here, or on this side you see a hollow structure because it's kind of empty over here. There's a hole in between. So you could have a solid or something that is hollow. And when it is hollow, it could be thin, and it could either be a closed contour, or like what you see over here, or it could have a C channel, which is called as a channel section, or let's say an I section that we talked about, or a Z section, etc. So all of them are open cross-section beams, and how they react to an application of a load in the form of a moment, which is a torque, or how they respond to a flexure, or how they respond to a shear, which is essentially a vertical load like this, or a horizontal load like this, but essentially which is perpendicular to the length of the beam. Similarly, in the case of the plate, it could be a shearing load like this on this side edge, or a shearing load like this. Both are essentially the shear that we are talking about over here. So how do we deal with those things is what we will look at. Then, so this will be almost the whole of the course, but it's also important for us at maybe towards the end, or as and when it is required during the introduction of these concepts, to very briefly touch upon certain aspects of the failure criteria, including fracture and fatigue. Fracture is when you have a damage that is occurring, and how it is initiated we want to find out, how it is growing. So we would like to explore those aspects, part of it. Then fatigue, essentially in terms of time varying loads, which are kind of cyclic in nature, not the impact kind of load, but which is kind of varying with time in a certain sinusoidal fashion, or a cosine fashion, or combinations of those with higher sines and cosine functions of multiple angles, etc. So in where the angle involved, of course, is omega times t. There's a certain frequency at which the load is applied, and t is the time. So essentially we're talking about that. So how do we deal with those things? So these are 3 F's that we have to be very careful about to make sure that our structure is avoiding these 3. Then I already mentioned to you elastic instability possibilities. We can go beyond that in terms of other kinds of instabilities which aircraft typically face, aeroelastic instabilities, which could be static instabilities like divergence, where you're trying to, let's say, deploy a control surface. It could be the aileron, elevator, or the rudder, and you try to change the angle of attack in a certain way of each one of those aerodynamic surfaces. It could be the wing, or the horizontal stabilizer, or the vertical stabilizer. But once you do that, if it's not aeroelastically stable, it can the twist, which is what you're changing to increase or decrease the angle of attack, can go on increasing. Okay, once you initiate it, it can go on increasing and eventually break. So those kinds of instabilities are not elastic instabilities, but aeroelastic instabilities, like divergence is one I mentioned, which is a static phenomena, and there's a dynamic phenomena called flutter, which many of you might have heard or even seen videos regarding. Then also very briefly we'll touch upon, so all these in yellow are not really part of your course, but they are kind of related to your course, and therefore we will take a glance at them rather than actually looking at mathematical models, etc., because each of them deserves a course by itself, at least one course. So testing, structural dynamics, structural testing. So this involves vibrations, both free vibrations and forced vibrations, then various kinds of experimental testing, and then what I talked to you just now about aeroelasticity. Then also most of what we develop as models eventually will get into computer programs, and most of them the numerical discretization is through finite element methods, and the various software which are standard and which many of you might have also used, like Abacus or ANSYS or Nastran and things like that, right? So we will not get into that, because again that itself deserves a course by itself, but we will see some of the variational principles that we develop as far as structural analysis is concerned, how those energy methods actually feed into this kind of a numerical discretization in order to solve such problems. And then of course we'll have towards the end certain parting remarks based on whatever we have done so far at that stage. And this is not to scare you, but just to show you what this assessment will not be like. Because I already told you we don't have any exams, leave alone a final exam. So our whole goal is to enjoy this process of learning about structural analysis, and what we take away from here in terms of how to utilize it in real life is what the takeaways will primarily be, which means that we will have assignments in every class, including today's. I will list out an assignment. Most of these will be simple, short ones. And as I already told you, you'll be working in teams. Of course, one of your classmates is yet to arrive, but once Patrick comes, all four of you will be working together on these problems. So we will be having a short presentation that you will give. I'm not so concerned about how well you design your presentation in terms of what animations you put into it and things like that. I'm more concerned about what you have learned from the previous class, how you have taken forward that knowledge applied to a particular problem, how you have utilized the various sources of knowledge that are available to you in terms of, let's say, internet sources, all these large language models, etc., how you have tried to give questions to it, what kind of questions, how did you change your questions, how did you interpret whatever response it gave, and if those responses were not to the direction in which you are trying to take it, how did you modify not only your prompt but also in terms of the very problem definition or the interpretation of the results. So these are the kinds of things I would like you to talk me around, and I will also try to do many of these homeworks along with you in parallel, and once you make your presentation, I'll try to come and give you a feedback in terms of how probably other ways of doing this. And many of these may not be unique ways of handling a problem. There could be multiple ways of approaching the problem, and each of them will have its own advantages and or disadvantages. So we will have an opportunity to compare them and try to utilize each of our understanding of that. So, and this is very, very important as part of this learning process. There is a very important thing that over a period of time we have gathered so much of information. Not all of that information may be appropriate or right for this particular course, and therefore there are certain concepts we might have to unlearn. And we will see that as we go. There are certain myths associated with structural analysis, and we will be busting some of those myths. But that doesn't mean that we are the final authority. Whatever we say is the ultimate. What we are going to do next is to learn the more correct. I'm not saying learn the correct, but I'm saying learn the more correct in terms of what today, as the state of the art, what is a better understanding of the same principles, of the same methodology, of the same interpretation of results. There are better ways of doing it, and are we using some of those latest techniques, not just because it is latest, but because it gives us some additional information in terms of better designing structures or better analyzing structures and helping the society in a particular way, or more particularly the aerospace ecosystem in a particular way. So it's a very important step. Many people forget that we need to unlearn certain concepts, wrong concepts that we have learned, or not so correct, because it's kind of harsh to put it as binary, wrong and right. It's more like a ladder where you're trying to approach the truth in grades and try to see. Sometimes you might take multiple steps on the ladder depending upon the new kind of knowledge system that comes up, but yet you would probably still have other rungs to rise to. So we are not leaving that alone. We are aware of that rather. So enhance the ability. So this is the third part to it. First you have unlearned, then you have learned something which is more correct. Then that alone again still not enough. Just to be proud of, I know the state of the art, but what is the use of it? Are you able to apply it to certain problems, either in this course or in future courses that you take at Georgia Tech, or maybe even when you go for your jobs or higher studies, are you able to take that forward? So that's what we will look at in terms of enhancing our own abilities to apply this assimilated knowledge to real life problems, practical problems. So with this, I think we'll come to today's homework. So the homework is based on something that you would have, many of you would have probably heard as part of your childhood, growing up as in kindergarten or from your parents. Aesop's fables are very, very famous, and one of them is the Hare and the Tortoise story, where they tried to have a race, and our grandparents or older people might say that the moral of the story is the slow and the steady win the race. But many of us are not so keen on being slow. Steady, we understand, yes, it might be useful to be committed to a certain thing up to a certain level in order to achieve something substantial. But is it necessary to be slow? Fast and steady might be even better. So there are extensions of this particular fable, in fact 3 episodes beyond what traditionally Aesop gave, and which are very, very relevant to all of life, but to structural analysis in particular. And this is the preamble to the homework that I'm going to give you. First, I will list out the understanding from the initial portion of this particular fable. What are the kind of takeaways? Again, as I said, there are no unique ways, and this is not the only thing. There are many other possibilities, but this is one proposition that I'm making just to get you started thinking on those lines. So what are we talking about over here? So you know, some of us have heard it from other people, or we have read about this story, this fable or fairy tale. And like most of the fairy tales, it starts with the phrase, once upon a time. So there already you have one variable that you typically deal with in structural analysis, especially when you're dealing with dynamic problems and dynamic loading, which is time. We already talked about it in today's class. We talked about spatial variables x1, x2, x3. We talked about time t. And when you're talking of once upon a time, you're establishing that yes, time can have keep going on either on the back or the front. One way is to explain things, but other way is to predict things for the future, or instead of predict, you are doing retrodict, which is essentially going from a particular point of time where you have the awareness of the status of the system, what had happened before that, what had it gone through, can you retrodict it? So this retrodiction and prediction, or prediction as we call it, are important parts of engineering over and above science of explanation. So scientists typically go for explanation. How is this thing happening? Based on that scientific knowledge, are we able to do prediction for the future and retrodiction for the past? Are we able to gather more information which makes our understanding more holistic, wholesome? So that is how, so as I said, this is just a phrase, not a full sentence. So there's a comma and the next line goes, typically you introduce the characters of this particular story, the tortoise and the hare, right? So like most biological systems, these are soft tissues. So from the point of view of what we are looking at, structural analysis, from our point of view, our perception, these are like elastic bodies. So unlike what you had studied as part of your dynamics course, where you predominantly dealt with rigid body dynamics, apart from particles of certain mass, you said you apply certain forces, what is the acceleration that results, what is the angular acceleration that results, how does the angular velocity change, how does the momentum change, etc., how does the impulse change. All these kinds of things that we were trying to deal with over there were with rigid bodies. But we know that in reality, no body is really rigid. Of course, relatively speaking, a stone is much more rigid compared to a biological system like this. So in that sense, yes. So these could be elastic bodies. Beyond a certain level, they could become plastic as well. In other words, permanent deformation could set in. But essentially, these are elastic bodies. But now, when you're talking about these two characters, like all physical entities we already saw, they have boundaries. That's why boundary value problems are important. They have spatial boundaries, they have temporal boundaries, and therefore seemingly unconnected with each other. So when they are not connected, so I have this body floating around in space over here, I have some other body floating around in space over here, these two are not directly interacting with each other. So in other words, there's no constraint from this or condition that this imposes on this or vice versa. So that's essentially what we are talking about over here, that we have a seemingly unconnected problem over here, and therefore there are no constraints. And constraints are very, very critical in any structural analysis problems, like the boundary conditions that you have. For example, this kind of a beam can be thought of as, let's say, a clamped beam, depending upon how the end conditions are. There could be on top of the window, there could be a label beam, which is essentially like a cantilever that you're talking about. In other words, one end is fixed, the other end is free. So essentially, you're talking about these kinds of constraints in terms of boundary conditions, in terms of initial conditions, and sometimes in terms of joints. So I could join this with a revolute joint, and they could be allowed to rotate with respect to each other, either in one direction or in two directions as well. So these kinds of things are all going to give you certain constraints that we have to deal with. The third thing, so you have an initial condition set up, you have introduced your characters, what a kind of bodies they are, and then now we are trying to get into the problem itself per se, in terms of what is the solution space in which we have to search for the right solution. So in other words, there are many possibilities. When there is an argument, you know that the winner of the argument is not by virtue of whether that fact is truthful or not. Usually it is based on whose debating skills are better. So irrespective of whether it's a fact or not, at least temporarily over a debate, it's usually the person with the better debating skills who ends up winning. So essentially, but they do consider, for an argument's sake, many different possibilities, and eventually agree with one of them, or say that we agree to disagree or whatever, right? So essentially what we are looking at from a mathematical perspective there is a certain feasible solution space that we are trying to search for. Yes, these are all solutions, potential solutions, which satisfy the constraints if they were, but only one of them or a few of them might be the actual possibilities. One of them, in the case of a single stable solution, there could be multi-stable kind of configurations where many possibilities are there. All of them could be possible at different points of time depending upon the initial condition, and one of them for that particular initial condition might be the right thing. So then argument is all about knowing about your feasible solution space. Next thing is, what are they arguing about? You have the initial condition set up, you have the characters introduced, you know what they are doing, and what are they arguing about? Who is faster? So that is what is the question. And once you have this notion of faster or fastest even, essentially you're looking at a stationary principle, a maxima or a minima of a certain quantity. For example, faster could mean maximizing the velocity or speed, magnitude of the velocity. So it could also mean minimizing the time taken from point A to point B. So it could be either posed as a maximization problem or a minimization problem, essentially a variational kind of a problem that we are talking about. But what we are trying to do in the case of an aircraft structural analysis is trying to, let's say, minimize the weight of a structural component, or let's say make it last much longer for a longer duration, so that it serves on the aircraft through the life of the aircraft itself, instead of having to replace it at a regular maintenance schedule in a maintenance repair and overhaul kind of a schedule. You want to avoid that. So there are many, many different ways in which the performance metrics for a structural component could be defined. Then, so this is as far as the problem definition is concerned, but then we have to go ahead and start working on the problem. The first thing that they do is, once they have argued about it, they have to decide on something, some common ground, and the common ground is in terms of the choice of the methodology. Yes, we want to find out who is faster. What is the way to find who is faster? You have to have a race, for example. So to settle with a race. So when you're racing with each other, so essentially what you're trying to do is to find the winner of the race, either one who reaches point A to point B in the shortest time, or in the fastest average speed. So essentially you're either maximizing the average speed, or you're minimizing the time taken between 2 points. So essentially you're putting it in the form of a variational principle, and this is where we will be taking a divergence from what we typically think of as Newtonian mechanics to Lagrangian mechanics or Hamiltonian mechanics, or total potential energy, how to minimize that, and things like that. All of these are equivalent to each other, but they are posed in different forms, and we will see the equivalence as well as their variation, and when one is more easier to use or more advantageous to use for various reasons, and what are the disadvantages as well. So we'll try to look at that. So the decision is to settle with a race, right? So then if you want to have a race, you also have to have certain conditions for the race. You have a start line, you have a finish line, and you have a path in between them. You have to choose that path, and for that you have to agree on a particular route. The final outcome of that is the winner of the race, whether it's the hare is the fastest or the tortoise is the fastest. But what we are interested more is in, at this stage, is in terms of agreeing on a particular route. Now when you're agreeing on a particular route, the first route that you take up is what you call as an initial guess to start iteration. So typically these problems are highly nonlinear, what we deal with, and you can't solve it as it is. So you have to have an iterative scheme, and there's an initial guess to arrive at that solution, and then you iterate so that a certain error function is minimized, and eventually you get to the actual solution. Now, once you have all this, the problem definition, the choice of the methodology, and then the initial guess as well, you have to get into the solution process. So this is where computers are really good at. So that the race is actually taking place, the solution process is running, and it's going to give a certain output. Okay. Now, if you look at this whole thing, you would see that as far as all these portions are concerned, this is essentially your problem formulation. And this is the problem solution. And you see that, unfortunately, most textbooks written traditionally were based on what they had read during the times when computers were very less utilized, and therefore their focus mostly is on the problem solution methodologies, the mathematics involved, analytical techniques for that, and maybe certain computational techniques in later books. But what is much, much more important is the problem formulation, because this lot of things, the software, if it is properly chosen and the inputs are given properly to it, it will take care of itself. But the input cannot be proper if your problem formulation has not happened properly. So this formulation is very, very critical part. It's the prerequisite for your problem solution, and that's where most of our focus in this course will be, in terms of understanding how to formulate various structural analysis for an aircraft, different, let's say take the wing, look at the spar or stringer or transverse rib, how do you define the problem for them, and then the choice of material, the choice of the thickness of those components, where you want to put holes, what kind of shape you need to have for them, etc. All of those are essentially going to be embedded into your problem formulation. Once you have that, the routine running of that can be taken care of by a solution process. This is not to kind of trivialize this, but to showcase the fact that this is also important. In fact, if this is not done, however well you do this, is of no use. It will be garbage in, garbage out. So you do not want that kind of a situation. So this we need to really spend a lot of time over. And as I was talking to you about earlier, when it was mostly manual labor, cranes came in and took off those jobs. Then when it was computational work, mostly, then the computers came in and took off this kind of job. Now AI systems are taking away a lot of this possibility also. Now even here, but you still need, at least at the stage at which many of the large language models are today, whether it is GPT-4 with Microsoft and or Google or various other players in the market, including OpenAI, from where GPT-4 comes, they're all primarily looking at the interfacing to this particular situation, where you're looking at how to pose the problem, that is the prompt engineering, and how to post-process whatever results it gives to interpret it and probably generate more questions from that in order to reach in the direction that you are trying to gain knowledge over. So that is essentially what we are trying to do over here. And as I said, this is just a part of that story, and it has to be kind of continued in terms of how we take that forward. So I think with this we'll probably stop today's class. We will take the other things up later on. I see that many of you are having jet lag, and probably you need to have good rest. It's kind of harsh on you to ask you to come to a class immediately after you have arrived from such a long journey, just that the course duration is very short, 10 weeks, and therefore we try to maximize this. But I'm sure as we go, you'll find the classes more and more interesting, and I would like to have it in a more interactive way, where you ask me questions, suggestions, interrupt me, find something that I'm doing wrong, point out, and we'll try to see, we'll correct it together, and we'll try to learn things together over there. So what I want you to do as part of your homework is to, you already saw this story that I showed you over here. Now, as I said, it is to be continued. Of course, you know what happened to that race. The hare ran for a certain distance, looked back, looked at the tortoise coming very, very slowly, and therefore became overconfident and just took some rest and went into deep sleep. And by the time the tortoise came in, passed the hare and reached the finish line, and that's why we were told that the slow and steady wins the race. But that is just the first episode of this story. As I told you, there are 3 more episodes to it. If you do a simple search on the internet, you will find those 3 stories as well. We will revisit it at the beginning of next class. After you make the presentation, I will also talk about it. But even though you'll get this yellow stuff on the internet, it is this orange stuff that I'm more interested in. How are you interpreting that for our structural analysis? How are you going to get? And as I said, there's no unique way of doing it, and my way is not necessarily a better way or best way. There could be many, many other ways. This is something that I just thought about this morning, and I just wrote this up. I had slight modifications for the other course as well that I'm teaching, the dynamics course of the same problem, because that also involves time and certain initial conditions, etc. So there are certain small variations in it, but for that most of these things are similar. So you're even welcome to interact with the other group and try to see what they find and what tools they use, what techniques they use. And of course, you are seniors, maybe you could help out with some of the other additional course knowledge that you have based on what you've learned over an extra year, and you could probably give them inputs as well. But the whole idea is, first of all, this story on this slide is not finished. I just told you orally, so there are more lines even in the first episode itself until slow and steady wins the race. But then what happens the second, third and fourth episodes, and most importantly, how do you interpret it for structural analysis. So this is what I want you to come back with, taking all potential resources that you have available, free resources. So I'm not asking you to pay for something, but essentially whatever is available open source, try to access those and try to see what best you can come out with in terms of the takeaways. Then you can present that at the beginning of the next class. Then I will try to present my version of it, and then we'll try to learn from each other and take up the other concepts of this course from there onwards. I'll also probably have a short review. You have had, all three of you have done the deformable bodies course, right? Because that was a prerequisite to this. So we will just, how long back was it? When did you guys do it? Which term? Last semester? Oh, okay. Okay, okay. Okay, okay. So I think at least for the benefit of some of you, I'll try to revise a few takeaways from that, so that that becomes the kind of the starting point for this course in terms of, then you'll understand why that was a prerequisite, because a lot of those concepts are going to be used in our derivations for structural analysis. Thank you. Yes, please. Make what available? Yeah, sure, I can do that. Yeah, I'll make the slides available. Also, the video recording will also be made available on the same platform, so you can take a look at that as well. Let me see.
For the videos that you posted for here, doesn't really bring me to anything.
Okay.